All right. Oh, cool. The camera's frozen. Let's fix that. All right. So we'll get a great point of view here. Okay. Welcome. So we're going to talk about more memory management. If we have extra time, we can go over Lab 4 stuff if you want. So let's get into more memory management and what the kernel actually uses in terms of algorithms, because it does not do the worst fit, first fit, or best fit. But it's good to know those things, but those are like the general problems. But hey, if you're the kernel, you know all of the sizes you're going to allocate. Since you're the kernel, you're managing your own memory. So you get to be a bit more clever. So in the kernel, and for this applies to, you can use this for user programs as well if you want. They do something called a buddy allocator, which is kind of a nice name, and it kind of lends itself to how this algorithm works. So it kind of restricts the problem, so it doesn't take general allocations of any size. It only takes allocations of powers of 2. So it only takes requests of powers of 2, so like 2, 4, 8, 16, 32, maybe the size of a page, maybe more, maybe less. That's the general idea. So it restricts allocations to a power of 2, and we'll see that that actually allows for a much more efficient implementation and a lot easier to kind of doing that merge step we were talking about before that we kind of hand waved about. So basically how it works is it's kind of recursive. It splits blocks into 2 until you can handle the request, and because it's powers of 2, if we split it in half, well, it creates 2 blocks of the same size, and then we can keep recursively doing that. And then since everything's a power of 2, it's really easy to merge stuff because you would merge essentially your buddy. So you got split off, so there's 2 of you, so now you have a buddy. So if both the buddies are free, you can merge back into 1. And what we also want to do too is enable really fast searching and merging. So we also don't want to search, do linear searches at every single element to figure out where we actually place an allocation. So to implement a buddy allocator, one thing you could do is use multiple lists. So you restrict the request to be like 2 to some power of k, where k could be, anywhere from 0, which would just be 1 byte, to some maximum number that you round up. So if you do that, your implementation would use n plus 1 free lists, so 1 for every single power of 2 of each size. So you'd have a separate linked list for each size. So you'd have a free list for everything of size 4, everything of size 8, everything of 16, and they're all the same size. So you don't have to bother going through all the list of elements that are the same, and you have like a logarithmic number of lists. So for some request that comes in, that's 2 to the power of k. So if it's a smaller, if it doesn't quite fit in, you just round up to the next power of 2 that it would fit. And then you search the free lists until you find a block big enough. For example, if there's a request of like 32 bytes that comes in, and we don't have any 32 byte free lists, you would look 1 level up until you find one. So maybe there's a 64 byte one free. Maybe there's a 128 byte one free. So as soon as you find the first free one, you would recursively divide it up until you get your required size, and then you would insert all the buddy blocks into the free list for whatever size you just split. And then for deallocations, well, every time you deallocate something, you'll have a buddy either before or after you. So if your buddy is free, well, then you can merge things back together. And then if you do a merge, you might do a recursive merge. So whatever sub-buddy you were before, you might have to merge that, and then you just go up and up and up. But you'd only do it for 1 of every element of the list for deallocations, which makes your life a lot simpler and it's a lot faster. Okay, So here's our scenario. So generally, the buddy allocator will have like a maximum size that it deals with. So in this case, let's just say our allocator is just dealing with 256 bytes of memory, mostly because I don't want to write out like 20 levels or something like that. So this is what it would look like. So anything in the black background means that it is actually used. It's not part of a free list. It's not used memory or anything. It's just kind of an illustration to show you what the original block was and then what all of our splits are. So we have a 256 byte big block of memory to do. Somewhere in our allocations, we had to split that up into 228 byte blocks. And then we split each 128 byte block into 64 byte blocks. And one of our allocations in the blue here filled up one of those blocks of 64 size. And then in our other 64 byte block, we split it off into two 32s. And the red allocation that used 32 bytes currently is used, so it's already allocated. And then it has a free 32 byte block there. So in this, we'd have in our implementation, there'd be a free list for every single level here. So there would be no free blocks of size 256, nothing free of 128. And for 64 byte blocks, there's 2 elements in the free list. And for the 32 byte list, there's 1 element in the free list. So if we get an allocation of size 28, where should it go? What should we do? Yeah, so we'd have to round 28 up to the next power of 2 because we are only dealing with powers of 2. So if we try and give it 16 bytes, that's not enough. So we have to round up. So we have to give it 32 bytes, round up. And in this scenario, hey, there's already a 32 byte block that is free. So here, same illustration, except in red just means it was split before. Anything in black text means it was free, and anything in blue means it's currently occupied. So in this, our 28 byte allocation, we would have to round up, and then there is something in our 32 byte free list, so we would do that allocation. So with that allocation of 28 bytes, how many bytes were essentially wasted? 4. Was that what? 4.5. So there are 4 bytes wasted. Was that internal or external fragmentation? Internal, because the memory allocator only deals with blocks of powers of 2. So there's no fragmentation between the blocks because they're all powers of 2. It's kind of nice. So there's no external fragmentation, but there's going to be internal fragmentation, and that's our trade-off. So that was our request. So 4 bytes, internal fragmentation. Yep.
Well, obviously not for this request, but say we got something that's like 15, round that to like 16. Would we split up the 32 into 2 different blocks?
Yeah.
Okay. But then what if that was like a really weird request where it was like the only one of size 16, and then you're going to have external fragmentation, so you're just going to have a leftover block of 16 that won't be used? Or is that's a problem, you just deal with it?
That's just something you deal with. Yeah, the question is, well, if you get a weird allocation of size 15, then you have to make a 16 block. Well, then there'd be a 16 block buddy along with it. And eventually, if you free that one, then you'd be able to coalesce the blocks and everything would be all good and you get that memory back. But if you don't do it, yeah, I guess you could call that external fragmentation if you would never, ever use a buddy again. So here's what happens. So now what would happen, so we did our 28 byte allocation, we had 4 bytes of internal fragmentation. So now we have a request coming in that is 32 bytes, and what should we do here? So is there any free 32 byte blocks? No. So what should I do? Yeah, I should look up, right? So I look up, I look if there's any free 64 byte blocks. There is. So what should I do? Yeah, I split into two 32-byte ones, so I create a buddy. So I would just pick this first 64-byte one. I would split it into two. So now I create two 32-byte blocks out of it, and I would use the first one or the second one, doesn't really matter, to actually do the allocation. So I split it up again. So now in our free list, there is one 32-byte block for the 32-byte block free list, and then free list for 64-byte blocks, there's one element in it because there's one free. And as a sanity check, everything should equal 128, all the free blocks and all the used blocks. So what's going to happen now if we free the size 64-byte block? Yep.
You can just use the last available 64.
We're freeing it. So we're going to free the blue one. Yep.
Oh,
It would become a 128 block.
Yeah. So I'd free the blue one, and now it would check its buddy. So its buddy's now free, so they can merge back together. So I freed this 64-byte one. So now there's two 64-byte ones free that are together because they were buddies. And because they were buddies, well, I can just merge them back together. And now I can have a free 128-byte block. Now, I can't have my free 256-byte block because I'm done at that point. Yep.
what if, so kind of like the example over here, you have 64, then you split it up into four 32s, and then you have the 32 on the left side allocated, 32 on the right side allocated. So technically you could merge the two middle ones together, but they're not buddies. How does that work?
Yeah, so you can only merge your buddy.
So like, even though technically there's a 64 continuous block of memory, this method wouldn't register that that exists.
Yeah, so the question is, so I assume, what about if we're in this situation where we have, two 64-byte blocks next to each other, they split into two 32s, so say we're using all 32s, and then eventually, we get somewhat unlucky, we free this one, so we can't merge them back together, and then we free this one, and we can't merge it back together. So in this case, there's a contiguous 64 bytes, all in a row that you might want to be able to merge, but because we're using the buddy algorithm, just to make things simple in terms of merging and not handling insanely complicated cases, you wouldn't merge those together because they're not buddies. So you'd only merge your buddy back together, which is why it's called the buddy algorithm. Yeah.
For like some sort of heuristic where they would want to like make sure that you and your buddy are filled up before we talk to like another pair, something like that.
Yeah, so if you implemented this, you might want to do some heuristic where you fill up buddies before or something like that. So, but in general, right, you can make heuristics, but they might not work. So just based off who uses it and their memory allocations, you might not be able to predict anything. But if you're the kernel, you can do some pretty good predictions because you kind of know how your memory works. Okay, I was just checking that wasn't me. Okay, so if we free this blue 64-byte block, then we just go ahead and merge them back together. Now we'd have a free 128-byte block. Okay, any questions about the buddy algorithm? It's pretty cool. Yep.
Out of curiosity, if you have that special case where you can't merge two 32 because they're not buddies, do you call this a fragmentation? Like if you want to try to put a 64 inside, and then you can't because even though there's like two available 32 bytes space, but you can't merge them.
Yeah, so the question is, well, would you still call that kind of external fragmentation because you have enough memory to satisfy the request, but they're not buddies, so it's not a big block. And yeah, you would call that external fragmentation. So that's kind of wasted space between them. So you don't get rid of all the external fragmentation, but you get rid of some of it. And you get internal fragmentation for your troubles. Yep.
Is this user space or kernel space?
So this can be implemented in either, because it's just a general memory allocation, but in general, the kernel uses this. So if you go read kernel code, they use this.
Okay, so does malloc use something like this as well, or?
So malloc generally doesn't. Malloc generally is more, I mean, there's lots of implementations, but generally it just has a free list and it lets you, it like does allocation that actually matches what you request.
Okay.
Because this is only powers of 2.
Okay.
So
So then is malloc like slower but wastes less memory or something like that?
yeah, it depends. So malloc sometimes is slower. So there's also lots of implementations of malloc. So if you like get into super critical performance ones, or I think the systems programming course here, they make you implement a better malloc that's more performant. So like if you look at Chrome too, so Chrome doesn't use the standard malloc you guys use. Chrome uses something called JE malloc, at least last time I checked, which is much faster. But you can swap in, do malloc, whatever you want. So that might be a fun lab in the future, but not this semester. I'm not in California anymore, thank God. Yeah. So yeah, there's always going to be trade-offs. So how fast it is versus how much fragmentation there is generally the big trade-off. So some of them you might not care about fragmentation. I do lots of really fast allocations, so or like slow ones that don't last that long. So maybe I want a different malloc implementation. So generally they're tailored. If you like get into super high performance code, maybe you just request a big block of memory from the operating system and you say, screw malloc, I'm going to manage my own memory. So that's also one thing you can do. But that's kind of like the ugly stuff you find when you actually start programming stuff that you actually care about the performance of. So we'll see one of the things. But first, yeah, buddy allocators are definitely used in Linux. They're fast and simple compared to the general case where you have to fill allocations of any size. It avoids some, but not all, external fragmentation by keeping the kind of free physical pages contiguous. And there's always going to be some internal fragmentation if your requests aren't powers of 2, because you always round up to the next power of 2. So there's going to be some internal fragmentation. Okay, the next one is slab allocators that take advantage of knowing that you allocate a lot of things that are all the same size. So if everything's the same size, well, you can just have one big pool where everything's the same size, and then you don't, and in that case, you definitely don't have any external fragmentation because you just keep track of the number of slots you have and what slots are free. And if you freeze something, you can just refill that slot. So all the things are kind of the same size. So for this implementation, you don't even need a linked list. You could just have a 1 bit for every single slot, and then that bit could be 0 if it's empty, 1 if it's used, and then really easy to see what's used and what's free. So this would completely eliminate internal fragmentation because everything's the same size, it would fit all in a slot. So when we get to the file system stuff, so I don't think you don't have a lab on it because that got eliminated, but in file systems, there's this one structure that's used a billion times called an inode. So you'll learn about an inode, but the kernel does some special optimizations with the inode because it allocates millions of these things. So every one of your files, your pipes and everything, well, every file and directory is represented by an inode. So since the kernel creates like millions of these things potentially, and they're all 128 bytes, it just has a pool that's all that size, so it just grabs them as it needs them and makes memory allocation a lot easier with that. So slab allocators are generally much, much better, but you have to know everything's the same size. So it's just going to be a cache of slots. So each allocation just corresponds to a slab slot. One slot holds one allocation. One slot holds one allocation. So instead of a linked list, just use a bitmap. So bit 0 corresponds to slot 1, bit 0 corresponds to slot 0, bit 1 corresponds to slot 1, and then bit, 1,000 corresponds to slot 1,000. So it's just a one-to-one relationship, and it's quite space efficient because it's just a bit for every slot. So for allocations, you just go ahead, search through that. Because it's a bitmap all close in memory, searching every element is going to be really, really fast. You can just check if there is any zeros in that byte or whatever to know that there is potentially a free slot there, and then you can figure out what bit it is and just return that. And then you just return the address to that slot because you know they're all the same size. And then for deallocations, you don't even have to delete the information or set it to 0 if you don't want to. Just set the bit as 0 and say that it is now free. So also what you could do is you can implement a slab on top of a buddy allocator. So for instance, if you still want a general algorithm, so you could have a buddy allocator and just say, hey, give me a giant block of memory, and I will essentially implement a slab using that giant block of memory. So this is kind of what it would look like. So consider we have two object sizes. We have A's and B's. So you might have, your buddy allocator, you might just get a fairly big block of memory. So you'd have a slab 1A for all objects of size A. And then say, because it's the power of 2, you can only fit 4 in there because they're kind of a weird size. So that black box would be internal fragmentation, and you wouldn't, so it would be some internal fragmentation. And then you could have another slab right beside it. That would be A2 that has the same issue, holds 4 A's and has some, holds 4 A's and has some internal fragmentation. And then maybe you have slabs for B's that actually nicely divide up the block. So you have 2 on this block, then you have 2 on 2B. So what you could also do is, in this case, you could reduce internal fragmentation if you didn't use different blocks for different slabs. So if you just had one big slab for A's, well, maybe I could fit, a 9th A there instead of only having 8 and having some internal fragmentation. Okay, so any questions about those types of allocators? Yep.
So slab A1 is the first cache for objects of A, or?
Yeah, so in this case, slab A1 there's 2 slabs for objects A. One that lives on this big block given by some buddy allocator, and then one that lives on this block. So we have 2 separate slabs here for A's. So you could make this better if we just, got a bigger block of memory from the buddy allocator and just had a single slab for A's. Maybe you can fit in a 9th one.
Oh, so you're saying like a buddy allocator would give you size, whatever that is.
Yes.
And then the slab is saying, I'm dealing with 4 objects of the same size, so I'm just going to allocate it as such.
Yeah. So in this picture, each of these little slabs, that block of memory would be given to you by some buddy allocator, and then you say, hey, I'm going to use this as a slab yourself. So you put it on top of it.
So slabs are usually used underneath like a buddy allocator or whatever.
Yeah, so you just have a buddy allocator that does all the allocations, and then you would just request a big block of memory and say, I know I'm going to use a lot of object A's, so I'll just use it as a slab.
Oh, I see. Okay.
So you might think, hey, I only need 4, and then you're like, oh, well, I used 5, so I need some more memory, and then I create another slab or something like that.
I see. Okay. But in the case of slab B, it's perfect because they're using like divisible by 2.
Yeah. Yeah, in this case, slab B actually fits the blocks. All right, any questions about that? Because that's pretty much memory allocation. Yep.
So slab method is used, like you said, like if you're doing the kernel, if they need to do like a lot of things at once that are the same, or
Yeah, so slabs are going to be used if you know you're going to have a lot of the same sized objects.
what would like a case of that be?
So, yeah, so in the kernel, there's a structure for you. I don't know what labs you had before. Maybe you have a linked list that has a bunch of nodes and you know the size of a node. So maybe you use a slab to just allocate nodes instead of using malloc or something like that. So you make it a lot faster because you know you're going to have like thousands or billions of nodes.
Wait, so do you do this like explicitly in your code?
Yeah, so you would have to do this explicitly in your code. This is part of the memory management stuff.
So like, what would you call like, is it just slab?
You'd have to implement it yourself.
Okay.
Yeah, so you'd have to implement it yourself or grab some library. So like this is also a very common implementation thing if you want to speed up your code. So like the Java implementation does stuff like this because object headers are all the same size and you know it's Java, so there's like thousands of objects even if you just print hello world. So it'll use essentially a slab for any object allocations and things like that.
And how does it check? Does it just like, does each slab have a little designated piece of memory that's an array, or how is it supposed to check if they're all?
Yeah, every slab would have a bitmap, which is just an array. So we'll see how to use a bitmap when we get to file systems.
And where would the bitmap be stored?
So stored just somewhere.
But so it's not necessarily on the slab. It could be somewhere totally different.
Yeah, it could be somewhere different, could be on the slab or before. Generally, with most of the memory allocators in user space, they just like add some accounting information to the beginning.
So that's how like when you free a pointer, malloc is able to say, oh, this pointer is of this size.
Yeah, yeah, yeah. So all that accounting information, that's why malloc, when you free, you don't need to say the size of the thing you're freeing because malloc knows the size because it's keeping track of it. Okay, cool. So we saw even more memory allocations. I'll take the rest of the class, I guess, to answer Lab 4 questions if we have any. So in the kernel, it restricted the problem for better memory management. So buddy allocator, real life example of that. We just restricted it to powers of 2. And then we saw a slab allocator that takes advantage of fixed size objects to reduce fragmentation. So let us switch back to this. So any Lab 4 questions we want to go over? Yeah.
We can use online resources to figure out how to get the exit code from the child, right? Because I don't know if we were taught
It's in the manual.
That's in the manual? Okay.
In the exit manual, yeah.
So, sorry, how to get the exit code from the child?
When a child exits, how are we supposed to get the exit code?
Okay, question. When the child exits, how are we supposed to get the exit code?
As the parent.
As the parent. All right, anyone?
You wait on it.
Wait.
But where does the exit code get returned?
In the W status.
Okay.
So we went over it in the code examples. And also, I saw people, so as part of that exit status thing, you have to make sure that that process, like if exited, if it doesn't exit, and that's not true, if you have an assert there or something, which asserts are good, and that gets triggered, you screwed up your file descriptors, I guarantee you. Yeah.
Why do we have to create all as a child and then wait instead of making the first child and wait and make second one and wait?
Okay, that's a good question. So the question is, why do I have to create all the why do I have to create all the children and then wait, as opposed to just creating a child, waiting, creating a child, waiting, creating a child, waiting? Yeah.
Because you need them to like pass information back and forth. They need to kind of be running in parallel almost, right?
Yeah, so answer was because they kind of need to all be running in parallel because they might be passing information back and forth between each other. And I assume that's what you were going to say too? Yeah? Yeah, so this is like the most common thing that I've seen that, hey, I run cat, or even the actual test was cat, what the std in thing is testing is if you type, hey, 1 okay, it should be repeated back to you immediately. And everything's still running at this point, right? If I'm running this. So what would happen is I type 1 in standard input, which is this cat. So this, and when I hit enter, it essentially flushes it. So this cat would read 1 and then write out 1. And then this cat is just sitting here doing read. So eventually the kernel is going to schedule that at some point, and it's going to call read, and then it's going to read 1 because the other one just wrote to it. And then it would write out 1. And then at some point, the kernel is going to schedule this cat, and it's reading from 0, and then it would read that 1, and then output it to the terminal. Yeah.
But like in the fork and then wait and the fork and the wait, wouldn't it like do the same thing? Shouldn't it do the same thing?
Okay, yeah, so the question is, if I do this instead, if I just had fork, wait, what would happen if I had that and I typed in 1 and I hit enter?
It would pass to the first cat, and first cat finishes, and then it like writes into some posture.
But if I'm here and I press 1, is the first cat finished? Yeah. Yeah, so if the first cat's finished, how could I do that? Yeah, so in this case, the first cat isn't finished. So the first cat just read a 1 and then outputted a 1, and then later it's not done. So I typed in a 2, it read a 2. So it's essentially, what's that stupid meme? This isn't done till I'm say it's done. So
But this doesn't work because of the initial cat. So like if after cat outputs and it finishes, then it will work.
yeah, so if you do, all right, so if I do 1, 2, 3 here, and I do fork, wait, and I type 1, enter, 2, enter, 3, enter, anyone want to tell me what I'm going to see? If I do fork, wait. Huh? If I do the same input here, I type 1, enter, 2, enter, 3, enter, and if your implementation is fork, wait, what's going to happen?
You wait for cat to terminate, but it will never terminate since it's still reading from the input. And then
If it terminates, you do 1, 2, 3, 1, 2, 3.
Yeah, so essentially, if I type 1, 2, 3, 1, 2, 3 and hit enter, well, it's going to stay there and just not do anything. If I finally hit Control D, well, then my first cat will finish, and then it would have read 1, 2, and 3 and written it out, but the next process didn't exist yet. So it just kind of goes, fills up a buffer, and then whenever that cat's finally done, then it would read 1, 2, 3 in a row. Then you'd wait for it to be done. So it would pass it to the next one. Then the next one would read 1, 2, 3, and then output 1, 2, 3 all in a row. But I don't want that because I want them all to be alive at the same time because that's how it behaves, right? They're all alive. They all still have output. And I want it to just flow like normal cat. Yeah.
So when if a process like if you create a pipe and then you fork, and then one process say like writes something and then dies, like what, like is the pipe still alive? Like is the data still in that buffer? If like one end of a pipe died, gets waited on, the whole thing, the whole pipe gets destroyed, or how does that work?
Here, let's go. So what's the question? We have,
Like you have two processes.
okay, so
by a pipe.
So we have two processes, P1, P2, and they're connected by a pipe. Oh, that's unfortunate. That's called the same thing. Let's just call the pipe B for fun.
And then like if say process one, like say maybe process one writes to it, or like the whole example there where like one, like you're writing to a pipe and then you exit
Yeah, so
Reads from it. Like, is that data still there?
yeah, so in this case, so I wrote the pipe as being essentially a B because it's essentially like a buffer. So what's going to happen is, well, this is actually connected to our normal standard in. So in this case, if I wait, I type a 1 and then hit enter, and then, right, this is cat, so as soon as you hit enter, your terminal goes ahead and flushes it. So it would read 1, then a new line, and then it would write it out because it's cat, that's what it does, and it would fill up essentially this little, you can think of it as just a pipe as being a buffer. So there's a file descriptor to read from the buffer, file descriptor to write to the buffer. So the first cat would just write to the buffer, and if you did the waiting thing, oops, this process does not exist yet. So if this process doesn't exist, there's nothing to call read on it. So the buffer just, that 1 just stays in the buffer, and then if I hit 2, I do a new line, then it just goes straight to the buffer. 3, new line, straight to the buffer. And then eventually, I'm going to close the file descriptor by hitting Control D. So that would essentially kill this process because now it's done. And the new cat would just read, whenever it does a read from that pipe, it would read, it actually might read them all in one big, like you do a read, it does a read of like a page size. So it would probably read all of this in one read call instead of like 3. So it would read everything.
And when does the like buffer disappear? As in, like, yeah, when does the pipe disappear?
So the pipe disappears when it's empty. There's nothing that could write to it, and it's empty.
Okay.
So the kernel would delete it. So the kernel only sends like the kind of end of file character if all the write file descriptors referring to that are closed. So no more data can come in. And then if you read all the data, then it's done. It can delete it. And then if you call read on it again, it would return 0 bytes read, meaning it's closed.
So you could like just keep like making pipes that are like buffers of size and just put like a single 1 in there and then delete your process. And then the kernel has to keep that buffer alive.
So if you delete your process, whenever you exit a process, all the file descriptors with that process get closed.
Oh, okay.
So you can't do that. Yeah.
In the lab you said, or in the lab handout it says, you have to return the exit code of the first
Yeah.
process.
Mm-hmm.
Meaning that the first process you create, the first process that failed.
First one that fails. First non.
Last one that gets run first.
First non-zero. So if it's like, so the example is, if you have, what time is it? Okay. So if you have like pipe, what is it? Invalid and false. Again, if someone's hard-coded these, please don't. If you do, I might just do like hidden test cases, so don't do that. don't force me to do that. So if you do this, the first non-zero one in order in the command line. So invalid comes first and then false. So if this one returns 2 and 1, well, I should return 2 in this case because it was first.
So it doesn't matter which one gets ran first, it's which one gets created first.
You have no idea what's going to get run first, right? So you have no idea what's going to get run first. You could wait on them in order if you want. That might be a smart thing to do. But one might finish before the other. It doesn't matter. You could wait on them in the reverse order. As long as you return the first one that dies, that's fine. But you can wait on them in whatever order you feel like, I guess.
So you can get all of the code and then just return the first one. Or you can just
Yeah.
wait on the first one and if it returns some.
Yeah, so you should wait on all of them, but because we want to be good parents, right? But so wait on all of them, but the exit status of pipe is the first failing one. Yeah.
So when we're saying first, we mean first in the list of arguments, not first in terms of time, right?
Yes, first in the list of arguments, not in terms of time, because unless you, well, you would know the time, kind of, if you called just plain old wait.
Yeah, but it's just like it changes. It's not consistent, right?
Yeah, it's not consistent because it's whatever one finishes first. But that's why I said in order of that, not finishing time. Yep.
I've heard passage saying that he asked a question on YouTube live, on the live stream.
Sorry?
He asked a question on the live stream.
Oh, crap.
Yeah.
Sorry, I didn't open it. What are the questions on that?
What the heck?
Was there a bot?
Why is there a bot?
Oh, sweet, there's a bot. I screwed up the chat. What's the question in the chat? Sorry, I screwed it up.
He asked why cat pipe is always expecting an input when the pipe is already closed.
All right, so can I explain why cat is always expecting input when the pipe is closed? Like this? Or wait, like this? So the pipe's not closed. Why would the pipe be closed? You are, yeah. So what pipe is closed here? There's no closed pipe, so there's two pipes. One, this pipe, its right end is this cat. Its read end, oh God, I can hear myself. Its read end is from this cat, and then there's another pipe, this pipe, whose right end is from this cat, and read end is going to this cat. So those should be the only ones with pipe file descriptors, and right now they're all open because whenever I type something, it goes through the pipe. So they're all open right now. And then if I hit Control D, then it causes a cascade of closing. So if I hit Control D, well, then cat is going to get, the first cat's going to get end of file, and then because that reaches end of file, that process terminates. And then when that process terminates, it closes all the file descriptors. So now the right end of the pipe is closed. So then now the kernel knows, as long as you manage your file descriptors, if that was the only right end of the pipe that was open, then the read end of the pipe is going to show as closed. So then the next cat can actually exit, and then the same thing's going to happen for the next pipe.
So is that why, like, in the test case, if you have, like, you name cat, is this why, like, if you don't close another instance of that pipe, it will hang?
Yeah, so you can actually create a process that you can create a cat that is not even a zombie, it's just like a waste. So what you can do, I wonder if we could program it, but so here, so say I have a cat process, and I created some type of pipe. So say this is my pipe. Maybe I should name it something different. Here, I'll just call it a buffer. And say I have FDs 1 and FDs 0. So if I do a system call on pipe, then that would be my two file descriptors returned. So this is the right end of the pipe, and this is the read end of the pipe. So for cat, it would be one of those is connected to it, hopefully, right? But I could do it where in my cat process, if I really screw it up, say 0 is just my terminal, so whatever, and then 1, actually no, let's do the other way. So let's say file descriptor 0 is the read end of the pipe. File descriptor 1 could be the terminal. File descriptor 2, that's standard error, so that could be the terminal 2. It doesn't really matter. So ideally in this case, if this is your cat process and then you close the right end of the pipe, then everything's good. The read end will appear closed after you finish reading all the data. But if you have screwed up when you do this and you haven't kept track of your file descriptors like I've been harping about, Well, what about if you don't keep track of your file descriptors, and this one has, say, you forgot to close, I don't know, some file descriptor 6, because some of you have some interesting code. So say you have file descriptor 6 open, and it's actually the right end of the pipe. Well, there's always going to be at least one file descriptor open to the right end of the pipe, so the read end's never going to look closed because that same process has the right end. So this will never close and never exit, and it won't be a zombie because it won't exit. It'll just sit there forever, and it can't do anything. Yeah.
About closing pipes. So in my implementation, like when a process, say like the first argument, it just needs to have the right end, like it needs to get standard out to the right end of the pipe. So I close the input part of that pipe.
Standard out to the right. Yeah, okay, yeah.
So I close the input of that pipe because I don't need that. But then I just like call exec CLP and transform the process. But like, how do I ever close that right end of the pipe, or do I just not bother closing it? Or
No, so before you exec CLP, the only file descriptors that should be open are 0, 1, and 2 in the child process. And if they're connected to a pipe, hopefully they're connected right, because if they're connected right, then eventually that read end is going to close if it's cat, and then cause that process to exit. And then if that process exits, as soon as it exits, it closes all the other file descriptors.
oh, so in my case, I only have the 3, but like the standard out, I've closed the normal standard out and I've replaced it with the pipe, and so that's fine.
Yeah.
When a process closes, it just closes all the 3, and so instead of closing the standard out, since it was connected to the pipe, it closed the pipe.
Yeah.
Okay.
Yeah, so that's why this works, right? It's a giant, giant cascade. So as soon as I hit end of file, from my terminal, so if I do this and I hit Control D, then that starts a big cascade. So the first process, cat would get 0 from read, so it'd say it's closed, so it would exit. Then as part of exiting that process, it would close all of its file descriptors, and in this case, one of the files, its standard output is the right end of the pipe, so it would close the right end of the pipe, and because as long as you were careful, that is the only file descriptor that points to the right end of the pipe. So if that process is gone, the right end of the pipe is gone, and then nothing else could write to it because it's the only one left. So then this next cat process would get, whenever it tries to read from the read end, it would say, hey, it's closed, and then it would go ahead, exit, and then when it exits, it would close the right end of the next pipe, and then the next cat would go ahead, read if there's any more data there, and then see it get closed, and then it would exit, outputting whatever it read, and then that process would be done, and then all your processes have finished, and they all finished nicely. Yeah, one of the most annoying errors is if you really screwed up all your file descriptors, some processes are going to get killed by a signal, which is really, really bad because none of the programs should get killed by a signal. So the only way the test will fail with a signal is if you essentially gave it an invalid file descriptor. So like you closed everything, and like you closed file descriptors 0, 1, and 2. So then as soon as it's tried to write from 1 or 0, it doesn't represent anything, so it dies. All right, any other quick questions? Lab 4, yeah.
This is about like the buddy allocator. You said you have to round up to like 2 to the power of k from 0 to n. What is n? Is that like
The biggest block you have.
which would be like pages, right?
Pages, or maybe you have multiple pages in a row.
Okay.
All right. Well, hopefully that answers Lab 4 questions. So just remember,